Thank you. Yeah. So my name is Chris McKinlay. I'm a principal engineer at Formation, and we mainly work on using reinforcement learning to optimize customer loyalty programs. And so I'm going to talk about some of the best practices we've adopted to write better machine learning code. So what are best practices in machine learning? There aren't really, I don't think there's a strong consensus on it. It's still like a very young field, relatively speaking, and it churns a lot. Even I think the criteria are up for debate. I mean, certainly correctness could be construed as a criteria, but for many machine learning algorithms, correctness is hard to even define properly. Performance is certainly a criteria, but I don't think the most important one. Testability, that's pretty compelling. But I think it's probably downstream of a more general criterion, which to me is probably the most important thing. So maintainability, that's what I would like to see. And we had a big issue earlier this year with maintainability of our code. So we'd identified a fairly simple version of our reinforcement learning problem that we thought we could solve with contextual bandits. And so we identified this library, Vowpal Wabbit, which had a pretty compelling out-of-the-box solution to the problem, and our data scientists understood how to use it. The problem was that we started building up a lot of code around it, and the code was very, very specific to VW, and it started to leak into other adjacent services. And this problem's been actually described before. This is a paper many of you probably heard of or read, and they outline this problem, referring to it as the Gluecode antipattern. And they define Gluecode as the code that you build up to get data in and out of general purpose machine learning frameworks. And interestingly enough, they have a recommended solution to the Gluecode problem, which is you should just re-implement the machine learning algorithm in your language of choice, in your architecture of choice, which to me is like not great advice to give a startup, especially if it's an algorithm of any complexity. It would take us probably better part of a year or more to re-implement the use case we have in VW, and there's no guarantee at the end of that the company would even be in the same place. I mean, applying reinforcement learning to customer relationships is like fraught with assumption churn, so we need to be somewhat flexible to that. So we didn't do that. Instead, what we did was just built up some fairly generic interfaces that can abstract away the library and work with other libraries as well, notably TensorFlow. And so I'm going to spend most of this talk just explaining how we used some design patterns in Haskell and the type system to facilitate that. And I'll talk a little bit about one particular use case, running EMR jobs to train a stochastic gradient descent process. Okay, so I think the main pattern that we use a lot, at least on my team, is called the handle pattern. But a lot of patterns in Haskell are kind of blogosphere phenomenons. It's not like there's any book for this. So it's been referred to as the service pattern before too. Basically, what it lets you do is encapsulate and hide state inside of handles. I'll explain what that means in a second. Provide functions to manipulate this directly, or rather than manipulating it directly. And finally, safely configure, create, and destroy handles. So if you were to replace handle with object and function with method, this would sound a lot like object-oriented programming. And maybe in some other use cases it is. In ours, because the state we're manipulating is inside of a C++ memory space, it doesn't really look like that, as you'll see. I should say, though, that doesn't mean this is a great thing to do. I think there's many ways to use Haskell that are much more principled. I'm sure lots of you have heard of monads, functors, applicatives, functor algebras, adjoint functors, recursion schemes, free monads, and all that stuff is really beautiful and great. The problem with machine learning is you're generally stuck with a very stateful object written in another language. and a lot of those things aren't really available to you. Okay, so here's a simple example of a handle called a source handle, which just represents a source of model files somewhere. And it has three functions that you can use. One, to load a model, meaning move a model file from some abstracted away location to a local directory, probably a temporary directory on the machine. You might supply a model version. If you don't, you'll get the newest version. If you do, and the version's there, you'll get that version. Similarly, saving and listing the versions available. And so we use this type of handle to abstract away the layout of model directories. And because we use TensorFlow serving at work a lot, which is a way to serve models, not just TensorFlow models, it expects model directories to be laid out with like a model and then subdirectories for each version and so on and so forth. So the code that generates these handles is responsible sort of maintaining the integrity of those versions and managing resource consumption, so bandwidth streaming files from S3 to disk and so forth. So that's a monomorphic handle, like there's no type variables. That's a little unusual. A lot of our use cases involve polymorphic handles. And in particular, this is a handle I'll spend a lot of the time in this talk talking about. So this represents a model that's been loaded into memory, and it's got 5 type parameters. It's got an input for learning, I, an input for scoring, J, which may be different from I, an output from the score, and a error type, and finally an M type, which is monadic. So the call sites will put constraints on M, like monad IO, monad mask, that type of thing. And here's how you configure one. So this is a type class to configure a model handle. And actually, properly speaking, it's a type family. So type families are a Haskell extension, language extension to GHC, rather, that we use that allows for some basic type level functions. And by that I mean, if C is some type that's implementing the class model config, then C gets to specify for itself what type the learning input is, the scoring input is, the output is, the error is, and the finalizer is the thing that's going to destroy the handle ultimately. And we'll provide a simple type alias model handle prime that's going to sort of, I guess you could say, quote unquote, call that type level function. And abstract away all of the dependencies behind a just simple model handle prime of CM. And, because it takes up a lot less room, I'm going to use that a lot in the rest of this talk. And in addition to the types, there's 2 functions that need to be implemented. I need to be able to create a model handle, and I need to be able to destroy a model handle or delete one. And here's where the constraints I mentioned earlier come in. So in order to create a model handle, your M has to implement monad IO, which means it has to have access to input and output of the program. And it has to also implement monad mask, which is a way of handling asynchronous exceptions. And because all of the actual types that implement this class are bindings to either VW or TensorFlow or XGBoost or whatnot, there's generally asynchronous exceptions are a fact of life that you have to deal with. So that's why those constraints are there. And then you can see create model handle just takes the configuration and generates inside that monad a tuple of the handle and the thing that will ultimately destroy the handle. And so you can see that being used. Here's a function from the API, which is an instance of what some people call like the bracket pattern. So what does it do? Well, it takes in one here an action, right? So some function that consumes the model handle and uses it to generate some result. So scores it on data, for example. And with model config is going to handle the safe creation of the handle, destruction of the handle, and then we'll run the action and give you the result back in the monad. And the way that it does that is using this function called bracket, which takes in a creator, a destructor, the action, and then runs the action. And you can see in our case, create model handle is pretty straightforward. Delete model handle looks a little funny because there's this thing called a type application. So this isn't a value per se, it's a type, because under the hood, Haskell is basically system F. This is sort of exploiting that. And the reason it needs to be there is because, if you remember, delete model has all this type information around C in it, but it doesn't actually eat C, the value, anywhere. So we're going to use this trick a bunch. And then the composing with the second and the first, or this is what's peeling off the finalizer from the tuple that was generated in create handle, and the actual handle. So this just takes the handle out of the tuple and then acts on the handle. OK, so let's see what one looks like. Here's an instance. Let's just configure a very simple univariate regression in TensorFlow. So y equals mx plus b. And I can do that by, this should probably be a new type, just wrapping some generic TensorFlow model config type, which will handle all of the framework level configuration. So what devices are we using? How are we logging out of TensorFlow? That type of thing. And simple is going to specify what the types it wants to use in its configuration are. And because it's going to take, when it's learning, inputs of x and y, this is a supervised learner, it's going to take a tuple of float primes, and it's going to output y hat, a single float prime. Or sorry, when it's scoring, it's going to consume a single float prime, which is x. And the reason they're float primes, where float prime just means tensor data float, is because I want this model to run inside of TensorFlow and consume data from within TensorFlow. I don't want to pipe necessarily data into that, and that's pretty common. But I'll actually generate outputs and errors outside of TensorFlow. And then the way that I specify my create model handle is I'll build a special function that simple is going to have to provide called make handle. And building simply means taking a build and running it inside a session. And in TensorFlow, at least the most prevalent bindings, build is just a state monad transformer on the actual graph state. So build is just a pure function that lets you specify which nodes attach to which, and that's it. Doesn't actually run the computation. Session runs the computation, and session itself is just a reader T. So it also notably provides the two constraints I care most about, right? So how would make handle actually work? Well, it's fairly straightforward. I know I'm going to need an x and a y for my inputs. TensorFlow has this fairly C-like way of specifying variable batch size, and I definitely want the inputs to my TensorFlow program to be variable. I don't want to hard code that stuff in the model definition itself. That's not a good place for that. So I'm going to make sure that the sizes of the batches of data coming in are variable. M and B are the two parameters that I need to optimize, right? So those are initialized variables, and then the rest is fairly straightforward, right? I'm going to write mx plus b equals y hat, see how far y hat is away from y, take the square of that, and then I'll take y hat and loss, and I'll render those two things, which just means specifying which devices, et cetera, those nodes would be rendered on. And that's 2/3 of my model handle right there. And then finally, I need to actually specify what an optimization step looks like. And because this model is fairly simple, we could just use vanilla gradient descent. If it were more complex, we might want something like Atom or something else, but we probably wouldn't want to hard code that in the model either. That would probably have to get pulled out and put into a configuration as well. But once I have my step, I can define my learn function, and I ran out of space in this slide, but creating the model handle from there is fairly straightforward. It's just taking score prime, learn prime, error prime, attaching them to inputs, and returning the handle. That's nice. Configuring a VW handle looks much, much different. Why is that? Well, VW is similar to TensorFlow in that it's written in C++ and it's basically designed around the notion of performing stochastic gradient descent online. But after that, it's completely different. First of all, there's no ability to design your own models. It's all done through twiddling of command line flags. So this is a CLI set of instructions to run a collaborative filtering algorithm on a classic data set called Movie Lens. I ran out of slide here. And everything that you would never need to pass into the algorithm has to be passed through the CLI. So all the hyperparameters around the learning, the decay rate, amount of L2 regularization, the number of bits in the underlying array that's being hashed to, even feature engineering. So I'm going to take two different namespaces of features and I'm going to multiply them all together and limit the rank of the output matrix. So a lot is forced to happen through the command line. This is more germane to our actual use case. So as I mentioned earlier, we use contextual bandits a lot. There's a particular kind of contextual bandit called an action-dependent function, or action-dependent feature bandit. And it, in this particular case, this set of commands is saying, let's train a contextual bandit configured to explore using the epsilon greedy algorithm with probability of 0.1. And it's applying a train set to that. And it's asking it to output predictions as it goes. So probably 1 in every 10 steps or something like that. And write those out along with some logging. And so this is the function that I want to spend most of the rest of the talk explaining to you how we productionize. But in order to do that, I'm going to start at a fairly low level, the FFI level for VW. So at the FFI level, all we really have is a pointer into VW memory, which I'll call a session as well. And we'll model it with just an opaque pointer alias, so there's no way to actually get any particular value out of this. But I'm going to wrap it inside a pointer. So this is a pretty common trick for FFI code in Haskell, and TensorFlow does this too. But the main difference is this is almost all I get from VW. I mean, I can get its notion of what it thinks the predict type should be, which is basically an enum over 10 or 12 things like string, float, int, what it thinks the input should be, its internal representation of that CLI, that command line set of flags, which is an untyped byte string, and that's it. That's all you get. And instead of a tensor, I'll have an example, which again is a pointer to memory. And I don't get much there either. This is pretty much the full API, right? I can pass in a byte string of options representing the command line flags, get my session. I can kill my session. If I have a session and I have a byte string, this time representing an actual VW formatted example, I can get access to that pointer. And if I have a session, I can destroy the pointer. And then I can learn on the pointer, which just means update the internal weights, doing, say, one gradient step. I can predict on the pointer, which doesn't actually mean predict. It just means make those updated weights back available to the example pointer so that I can then do something with it, right? Both of these have the same type signature. And then finally, I can get some basic statistics, like the number of features seen and that type of thing out of the session. So if I add 2 brackets to those things, with session and with example, I have just enough to be dangerous. So here's a simple function using those two. So I'm going to take in my byte string of options. I'm going to take in something that looks like one of those learn or predict calls, but could in fact be sequenced learn and then predict, or predict and then learn. Some kind of extractor, some way to read that pointer and get an output out of it. And then I'm going to pass it a list of untyped data inputs of some sort. And then here's how I run it. So I'll pass the options to my withSession function, and then I get back a session, which I can then pass to withExample for each data in the list, and then I can act on it. And in practice, what does that look like? So here's some data. VW uses the old lib SVM format, so that's why it looks funny. But basically, this is a label, and these are namespaces, and in each namespace, these are features. And here's my command line arguments, and here's my action, and here's my extractor. And when I run that, I actually get a probability. And that's because VW has inferred that what I really want to do here is run a logistic regressor. So this is what it thinks the probability of these inputs being 1 is. And if I were to run this on the same input replicated 5 times, you'd see the probabilities creeping closer and closer to 1 as I overfit the hell out of this one example. So this is obviously pretty limited and not what you'd want for a high-level API. The most notable problem is there's very little static assurance or compile time assurance of anything. The byte string for the options is untyped. The byte string for the input is untyped. You have no confirmation that what VW is expecting in terms of input type is what you're actually giving it in terms of input type. So let's just quickly solve all of that. And one way we can do that is by just noting that this looks very sort of CPS or continuation passing style, right? I've got a bunch of unnamed lambdas nested inside one another. I can use what's called a continuation monad to model that carefully. And all a continuation monad or monad transformer does is takes a function that looks like this. And what this type signature says is, if you give me an E to monad of O, then I will give you a monad of O. Which, if you're familiar with Yoneda lemma, is basically the same as having an E modulo fuzzy reasoning. And if I specialize that using some applications to the types I care about, we get this, which looks very, very similar to with example, right? In fact, the second half of with example looks just like the first half of my cont constructor, which means if I just compose them, I can replace this part with something more general that's still polymorphic over the output type and lets me structure things more nicely. So I can take that type and abstract it. And now I have something I can work with. I can place constraints on. So it's just simply a type that represents what we had here, except instead of forcing it to be a byte string, I'm going to loosen that up so I can take more structured inputs, other types of input. And the first thing I can do with that is differentiate between things that are serializing data into example pointers, but never do any output. They never read stuff out of the pointer. So that means if I have a function that does that, it really should work with continuations for all output types. It shouldn't care what the output type is, because it never does anything with the example. It's just on the input side, right? So that's nice. And then maybe I'll take the one other thing that we saw a couple times, where I've got either learn or predict, and then some kind of extractor, and I want to run both of those. So I can also lift that into a VW. And in this case, the input type and the serialization type are the same. And once I have those two, if I go back to process lines, it looks a little bit different. Instead of that nested sequence of continuations, I just have one little monadic statement. And I've got my serialized function and my lift function. And that's nice. I don't know if that was worth all that effort, but this isn't really the target audience. Process lines is like a throwaway piece of code. What actually we get to do is construct more complex serializers and use the types of VW to impose constraints on that configuration when I generate model handles. That's really what I'm after. I mentioned a moment ago that our main use case was what's called action-dependent features. So that is a very complex serializer, which we're able to sort of nicely capture using continuation passing style. And this is almost perverse, but the way that action-dependent features work is it actually takes 2 example pointers and a list of byte strings, which needs to be non-empty. And this represents really morally a single input, a single example. And what it's going to do is look at the head of the byte string, serialize that into a pointer, run learn on it, get another pointer, take the rest of the byte strings, BS, serialize all of them into pointers, run learn on all of those pointers, but throw them all out until it gets to the end of the list, then serialize a empty byte string, and then return E1 and E2, because of course. It's nice to have some structured code to help you to reason about stuff like that. And finally, the last thing that we do is when we configure a model, I have a couple of type parameters, right? And I can enforce that, like, the thing that learns never generates any output, because it shouldn't, right? It should be a pure I/O action. I can enforce that the thing that's serializing examples into the learn function, because recall my handle takes different learn from score types, so I can enforce that that actually isn't touching the output. And I can enforce that something that's actually going to generate output isn't doing anything else with it. And it has its own serializer. And so when I put all that together, I can build a model config fairly nicely. One thing to note is my E is actually the example type. So this is how I differentiate between different kinds of bandit. But all bandits, all models have the same statistics. So that's the error that my model handle generates is always this fairly large type called statistics. And I think in the interest of time, I will skip the details of the handle creation and go straight to using, which is more fun. So I'm going to talk a little bit about how we put together a harness that can run SGD jobs using constraint kinds and that kind of thing. And one thing we use a fair amount at work is colloquially referred to as a has pattern, which comes from lens library. So lenses are used a lot in Haskell to access data. And what a has_foo class does is it simply says S has a lens prime between itself and foo, which basically means it has a setter, or sorry, rather a getter. It can get a foo out, and if it has a foo, it can update S's. And there's a similar version for prisms, and one thing that we use is a slightly weaker version, which just includes the getter version. So if I have an S, that means I can somehow get a foo, and I'm going to need that in a moment. And actually, we're going to make it a little more general so that we're not hard-coded to foos, but any A. So get A is simply a function from S to A, morally. Okay, let's talk about our SGD harness. So first off, I'm going to run SGD online, so to speak, which means like I'm going to take a bunch of learning steps and then do a few holdout steps, and then take more learning steps and then do more holdout steps. Rather than doing all the holdout at the end, which you might be more used to. And that's a good fit for a couple reasons, but it means that we're going to log the learning stuff separately from the holdout stuff and put them together at the end. So what does our learning logger look like? Well, it needs to know the number of examples it's seen so far, and the loss that the model's accrued, the training error. And I'm going to give it a monoid, which I won't talk about much, but because the model is C++ code, I need to rely on its error type from that handle to tell me how it's doing, which means I need to have the model handle prime and the input of that handle, whatever it is. And then I can pass it one of these learning info types, and then because it's going to need to access either a TensorFlow session or I/O in VW case, it's going to give me back an M of linfo. And so once I have that logger type, I can give you an example, and you can see where these constraints are getting used. So if I have, what's this type signature saying? It's basically saying, for all configuration types and all monads such that C is in fact a configuration for some kind of model. And the error type of that model is able to generate a loss, because in the case of VW, the error type is a very large statistics type. It has lots of stuff in it, right? Not just a loss. In TensorFlow case, because we can really specify exactly what the model does, I might be able to just make the error loss directly. But this function doesn't care about that, right? As long as these constraints are satisfied, it can do its job. It says, OK, well, tell me how verbose you want me to be, how often you want me to update, and I'll check if it's time to do that. And what does do that mean? Well, it simply means call the error function of the handle on the input, get the error, use the getLoss constraint to update the loss, and then log it somewhere. Probably need monad.io for that, and then lift the result back into the M specified by the model. And so I can start to put this together with other stuff to run a pipeline of actions. And one way to do that in Haskell is to use a conduit library, which is sort of resource managed streams, very similar to FS2 if you're a Scala person. And it revolves around this type conduit T, which is a stream of inputs, a stream of outputs, some sort of monadic effect, and then some sort of result which lives inside the monad. And I'm just aliasing here so I can fit everything on the slide. And so here's what learn looks like. If I have my model configuration, then and I have a model handle and a logger type, then what can I do? I can consume inputs, and in this case, inputs are just tuples. So this is just the example number and the actual input type, which of course depends on C itself. And I can grab the input, pipe it into the handle and learn on it, lift the result into the conduit, and iter_m looks like that. So it's just going to run a IO or M of unit action a whole bunch of times and keep returning the A's. And then I can use my logger, after it consumes the handle, to scan over that input of A's and aggregate them into that L info type. And to begin with, because it has a monoid, it'll just be the default. So this is pretty nice. You can also see that I have tons of constraints on C, but C as a value doesn't appear anywhere. OK, let's do the same for scoring. OK, but scoring is a little bit different because I'm going to do it outside of the model. I'll do it in Haskell. And that's nice because it lets me enforce even playing field on different models, right? It'd be very hard to compare a TensorFlow contextual bandit with a VW contextual bandit if I'm letting them both do their own holdout scoring. However, in order to do that, I need to specify some additional constraints. So first of all, I need some way to get a scoring input from a learning input. And I don't want to have to do that in data. I don't want to be reformatting every 10th data type or every nth data type when I run this job. If there's a model-dependent way to actually just throw out the label from the learning input somehow and pass just the features to the scoring input. And I have to do that because I've got two different types for learning and scoring. So in that simple TensorFlow case we saw, get might just be first, right? Because I had a tuple and I want to drop one. But in a more complex case, this might be something completely different. So I'm going to encode that in what's called a constraint. And in order to do that, I need a language extension called constraint kinds, which just simply lets you sort of manipulate constraints to functions. So the second constraint I'll need is actually to do the assessment, the holdout assessment. And in order to do that, I need to take the output of the model and figure out what action it chose. It's got, let's say, a number of different things it could select in order to do. And because this is a reinforcement learning algorithm, we don't necessarily know the world's response to that action if the model had chosen it. But I can get the action still. And from the input, if I can get a special type called an ARP, which just stands for action reward probability. If I can get that type, then I can use an inverse propensity sampler to estimate what the cost would be, hence the term IPS. So this is a constraint that lets me run an inverse propensity sampler. And when I add those constraints to my monad IO constraint, I can actually do holdout. And so the way I do that is I just score the input. So where score just looks at the data, and then it uses that get to extract the scoring input from what is actually a learning input, right? Pass the scoring input to the score function on the handle so the types line up. Lift all of that into the conduit, and I'll return that along with the original data so that I can update my holdout on that. And so what does holdout update look like? Like this. So I've dropped the holdout constraint because I don't need it anymore, but I still need the IPS constraint. And what I'm going to do with the constraint is consume these triples, and I'm going to run IPS on the input data and the output action from the model, and then I'm just going to aggregate that using the monoid instance for scoring info. And that's it. So when I put all of that together, and I'm not going to go too much into how IPS is implemented, but it needs constraints in order to be able to actually compare the things. Once I put all that together, I can define a logger that's just going to tell me, okay, how many times do you want to actually score the thing versus learn, and give me two loggers, one for learning and one for scoring. I can put those into a fold. So I'll issue a 0 ID to start. So index starts at 0. Depending on the strategy, I'll generate eithers of learning, scoring. I'll run holdout or learn, and then I'll gather at the very end. Holdout or learn is just simply going to look at whether the either is a left or right and decide what to do. And here's where that type application gets passed, because recall, learn and holdout don't actually eat C. And then gather just takes those eithers and then aggregates the appropriate logger on the left or right and returns a product. And then when I have all of that, I can put it together in what I told you I was going to tell you, which is this with model config function, right? That API that we looked at on like slide 10. And recall that with model config has a monad mask constraint, and none of the other code you just saw has any, so that's why that's there. And in order to lift everything into monad mask, I need something slightly technical called lift with from transcontrol. But basically, it's just going to, for free, give you asynchronous exception handling and all of that interior code, which didn't actually have that constraint. And it's going to consume that action function. And all act does is run train fold, which we just saw, get all of that, and then it's going to check the very, very last one. And if there's a info there, it will log it. And if there isn't, it'll just log a blank and return. And so this thing can run in a bunch of different places. In a Kubernetes cluster with access to TensorFlow, it could run in a Hadoop cluster, so on and so forth. So that's it. I don't know, one moral is I Googled machine learning architecture when I was preparing for this talk, and I love that the very top hit is actually talking about liberating architects. So I don't really think there's a lot of good literature on machine learning architecture. And you should feel free to make up your own things and question authority. Here are the links I promised you, and that's me. Yeah, thank you.
Awesome. Thank you, Chris. That was great. All the complexity of machine learning and all the dense obscurity of Haskell all in one talk.
A mile a minute. Yeah.
Yeah. So we do have a few minutes for questions before running along to the next talk. So if are there any questions?
I feel like some kind of apocrypha in the Haskell ecosystem around like the handle pattern specifically, and passing all of this stuff around in records is potentially more like of a speed problem relative to putting more stuff in the type classes. Have you noticed that the handle pattern has been like good for you as you've written code like this, which I imagine has speed implications when you run it, or like?
We never A/B'd against the sort of type class version of it, so I can't really answer your question authoritatively, but I would say the culture at my work is pretty anti-type class unless it's like really necessary. So we didn't go there. Yeah. Yeah.
Why is the scoring input type different from the training input type, and is there a relationship?
Yeah, this is a great question. So the reason is for some models it really just has to be. So for certain reinforcement learning models, the scoring isn't just adding a label to the training. It's much more like adding probabilities of different things to all the different possibilities. Another reason is we want to make sure that models that are going to serve are not accidentally seeing labeled data. And in Vowpal Wabbit's case, it will silently consume labels and update itself without telling you, unless you're careful. Yeah.
Okay.
Cool. Thank you.
Thanks, Chris.